record button. Okay. Okay. So I guess this is now for you guys at the off season, right? We just finished the last regional, and now we have nothing to do for a while. But for our top team, they will be doing the next level of contest on April 22nd, right in the middle of exam week, the North American Divisional Championship. So we are going to be preparing for that. But for you guys, if you want to play, um, there is this thing called the Google Code Jam. Now, Google Code Jam is a contest that's open to basically everybody in the world, not just university students. Okay, so even I can compete, although it's probably not so good because I'm too old and useless. So the qualification round starts on this Friday at 7 a.m., and it lasts for 30 hours. And typically, there'll be some problems. You can actually go and look at the previous rounds. Okay, so this is 2021 schedule. I registered, and you can look at the archive to see some past problems. And usually, let's see, 2021 terms, um, attendance at the. So they usually say that the first, uh, they don't, they probably don't say it very much here, but basically there are problems, and the problems there will be each problem there might have multiple parts. Some part maybe will work on smaller inputs. Some parts requires you to solve the problem for bigger inputs, and each problem will have a certain number of points. They will tell you in advance that if you solve this size, this part, you'll get this many points. Otherwise, you get the other points. Some problems are worth more points. Some problems are worth fewer points. And basically, they will publish during the contest. They will say anybody that gets, I don't know, 35 points or more will move to the next section, next step. Okay, so for the qualification round, it's actually done for 30 hours because they want to make it available regardless of where you actually are in the world. So you don't have to do it in the middle of the night. And usually, if you do maybe two problems or one and a half problems, it's probably enough to move on. And there's no ranking in terms. You don't have to be the top whatever to move on. But then after that, round one, then it's timed, and then also you have to be the top whatever number of people to move on, etc. Okay, so if you're starting out, this may be a little bit too hard, but it wouldn't hurt to look at it. Usually, for each even if you're starting out, the problems, the first couple of problems for the small inputs, it's probably still approachable. If you didn't know, if you think that this is too hard, another competition that is a little bit easier. It's called Google Kickstart, and this is something that's for people that are maybe starting competitive programming, but also it says that while getting a sample of coding skills, programming skills needed for technical career at Google, if you do well enough, they will actually some of these recruiters will actually send you an email and ask you if you're interested in sending your resume and so on. And for Kickstart, it is actually a lot easier in terms of getting in. There's sort of rounds all the time. There's one that's coming in April. There's one I think that just happened last week. And basically, there's once a month, and it doesn't really matter if you have done round A. You can do any one of them. And the problems are generally they're not simple, they're not trivial, but they're a lot easier than the harder contest Google Code Jam. So you can go to archive and see, let's say, just click on a random one, you can see these problems, and it will tell you what the problem is, and you have to code in this editor. But of course, you can code in whatever editor you want and upload the file if you want. So there will be some problem, just like any programming contest problem, there'll be some problem, there'll be some input specification, there'll be some output specification, and then they will say test set one, you have only, the size is only 1,000, and then test set 2 is a little bit bigger, and then the sample inputs and so on. And then after the contest, you can click on analysis and it will kind of explain to you how to solve the problem. Okay, so anyway, this Friday is the Google Code Jam, and if you're interested, we can talk about it on Discord while we're doing it. There's no prohibition about people discussing how to do the problems as long as you don't post the solutions for the qualification round. After that, then you're supposed to do everything by yourself. Okay. Okay. So anyway, that's the what's coming in terms of contest schedule. I guess I was the only one that did anything, but that's okay. Maybe people are busy with exams. So I picked 5 problems here, and they all have a theme. So the idea is that what I want to do now is I want to have a theme every week. And these 5 problems, maybe I will show the problems, talk about solutions, and then we'll talk about what the theme is. Okay, so the first problem, I don't know how many of you actually read the problems because it doesn't look like people have joined. So I'm just going to quickly explain what the problem is. So this is an algorithm that's kind of buried inside Quicksort. If you're familiar with Quicksort, what happened is that you take an array and you choose some pivot, call it P, and then somehow you put the P somewhere in the middle, hopefully, and then all the things to the left of it are less than equal to P, and all the things to the right of it are greater than or equal to pivot. Okay, so for example, but now what they're telling you is, here's the actual array. So the array after you've done the partition, this is what it looks like. The question is, which one of these numbers could be a pivot? So for example, 4 could be a pivot because everything to the left are less than 4, less than or equal to 4. Everything to the right are bigger than 4. So 4 is a potential pivot. So it's 3, so it's 8. But for example, 1 is not a pivot because things to the left, it's not smaller than 1. So your question is, given a particular array, which one of these are possible pivots and which ones are not? Okay. So that's the problem. Now, of course, you might say, well, okay, for each number, you can just go and say, well, if I want to know whether 7 is a possible pivot, what do? I look at the numbers on the left, I look at numbers on the right, check all of them. If it works, it works. But the problem is, if you do it this way, then you're looking at basically a linear scan for each element, and then basically you do it n times. So it'll be big O of n squared if you do it this way. So for each element, you look to the left, look to the right, and see if the property holds. And if you do that, then I guess that's good enough. But the problem is, if you go down, the input basically is an integer, and the size of this list is an integer n, which is at least 3 and up to 100,000. Okay. So if you have n squared, that's not good enough. And the CPU limit is 1 second, so there's no way n squared will work. Okay, so what are you supposed to output? Output how many numbers can be the pivot. So you don't have to say which ones, you just have to say how many. Okay, so in this case, there's 3 possible ones. It turns out that 3, 4, and 8 can all be pivots. And in this case, it turns out that all of these 2, 3, 4, 5 can all be pivots, and so can 1. These 5 numbers can all be pivots. Okay. All right. So that's the first problem. Anybody have any idea what we should try to do?
I started working on this one and I think I'm close to getting it, but it's not working. But
Okay.
I was just doing like every time I take one in, so I take in 2 as the first number. There's nothing to compare with it. And then I take in 1. And if the numbers in front of, so I would go through like the vector in front of 1. And if any of the numbers are bigger, then the number that's bigger can't be a pivot and 1 can't be a pivot.
Okay.
And then I don't have to check if they're the ones on the right hand side are bigger because I should already catch all of those as I go through.
Okay. So
I hope.
we go this way. So
Yeah.
so you start looking at 2.
Yeah.
Now, at this point, do you know anything about 2? You don't know
No.
anything, but you know that there's nothing to the left, but you don't know anything about what's to the right.
Yeah.
Okay. Now you see a 1. What is the next thing that you do?
I checked to see if 2 is bigger than 1. And it
Okay.
is. So 2 can't be a pivot and neither can 1.
Okay. So now what? So now I go to here.
Yeah.
What do I do now?
So now we check if 2 is bigger and it's not, and then check if 1 is bigger and it's not. So 3 counts.
Possibly, but you don't know what's happening here yet.
For now it counts.
Okay. Then you see 4.
And then do the same thing. So 2's not bigger, 1's not bigger, 3's
Okay.
not bigger.
Now, so now here's the problem, I guess. The problem that you have is every time you get to a new one, you're going to check everybody in front of you.
Yeah.
Right? So if you do it this way, the problem is not that you can't get it right, but the problem is you can't run it in time.
Okay.
Because it's n squared time. Okay. Now, let me refine your idea a little bit. Okay. So we start from the beginning. 2, well, there's nothing to compare to, so 2 is still okay for now. I'll just put an underscore here to say it's still okay. 1, I compare to the one before, and it's not okay, so this is no longer okay. This is no longer okay. Right? And now I look at this one and I say, well, let's compare to the stuff before. Now, not only did you know that 1 and 2 are not okay, you have something else. You know that to your left, the maximum is 2.
Okay, I was just thinking of that actually when I said that.
So when you compare 3 with the maximum, then 3 is okay. When you compare 3 with 2, not only do you know that 3 is okay against 2, you also know that 3 is okay against everything else because 2 is the maximum. So now you come here, but you have to remember to update the maximum to 3 now because you just saw 3. 4 compared to the maximum is okay, right? So that's good. And now you go update the maximum is 4. You look at 7. 7 is bigger than 4, so you're still okay. And you update the maximum. 5, what do you know? 5 is not bigger than or equal to the maximum, so you know that this 5 cannot be. 6 cannot be for the same reason, and 8 maybe. And you update the maximum. Actually, it doesn't matter if you update it because you're done. Okay. Do you understand what I'm doing?
Yeah, that makes sense.
Okay. So now, what have we managed to do? Let me just draw things a little bit differently. I have managed to eliminate 2 and 1. Well, actually, I haven't managed to eliminate 2 because right now, I'm just saying if I am bigger than, if I'm not bigger than or equal to what's to my left. So for 2, I cannot do anything because there's nothing to my left. 1 for sure it fails. 3 it's okay. 4 is okay. 7 is okay. 5, 6 fails, and 8 is still okay. Okay, do you agree so far?
Yeah.
Okay, so now what is the important thing? Oops, oh shit, Okay, let me draw this again. There's no undo here. Watch me struggle with technology. Okay, okay, I already switched the color. Black is, okay, what the heck am I doing?
I think 2 you wanted to be included in
okay.
the good group
That's
for
right.
now.
That's right. And this is so far possibly good. Okay, so red means it's maybe good, bad. Black is definitely bad. Okay, and the important thing is, how did I manage to do this? I managed to do this in linear time by doing scan from left to right. Okay. Now, what have I done? What I have done is to make sure that the things to my left are less than or equal to me. I know nothing about what's to my right. So what should I do now?
Well, technically, could you have ruled out the max each time that the number was smaller than the max? Like 2 and 7 should have been ruled out because we know that if there was a number on its right that's smaller, then it has numbers on the right.
Yeah, I guess
you
you have to keep remembering this, but the problem is, you know, let's say when you scan this way, you have I don't know, let's say 6 and then 7. So when you scan this way, and then you see a 5. Okay. So now your current, when you scan this way, your maximum will be 6 and then 7. And then when you see the 5, then you say, oh, 7 is ruled out. But now you have to go back and rule this out too. But you already lost the maximum. You didn't know the 6 was a problem too.
That's what I messed up. Thank you. Because
Okay,
I'm
so
realizing why I have 4 now showing up.
okay. So now what? I keep on erasing this stupid thing. There's no undo. Okay. Anyway, so if I scan this way, I can see which ones are violating the left-hand side being smaller or equal to. So what do? I scan the other way. And this time, instead of keeping the max, I keep the min. Okay, so I scan this way. 8 is still good. So I don't know which color was I using for good. Good is red. Okay. 8 was good. So min is 8. 6 is smaller than 8, so that's still good. Now min is 6. 5 is smaller, so the 5 is, so this is still good. 7, 7 is no good because 7 is, I'll just cross it out. Okay, 7 is no good because 7 is not smaller than 5. 4 is okay, and this time min is 4. 3 is okay. 1 is okay. And 2 is not okay. Right? So if you scan the other way, you'll get a list of things that are okay on the right-hand side. So now what do? You combine the two lists, and if it's okay on both sides, then it is a good one. Otherwise, it's bad. Does that make sense?
Yeah, that makes sense.
So the idea is that basically the idea is this. If you want to know if you have a pivot here, and you want to know if everything to your left is less than equal to P, you don't literally need to compare with everything, as long as you know what is the maximum here. The maximum better be less than or equal to P. And over here, you want everything to be greater than P. Whoops, the other way around. I didn't show it properly. You want everything to be greater than P. So what do you need? You don't need to compare with everybody. You just need to know that the minimum of this chunk is greater than P. And how do you compute the minimum of all the different chunks? Well, if you want to compute a minimum of these, the chunk on the left, basically you work backwards, and every time you can build up the current minimum as you go, basically in one scan. Similarly, if you want to keep the running maximum on the left side, you build it this way. And that basically allows you to do it in linear time. Okay. Any questions or comments before I show you the code? Okay, so then I'm gonna show you my code. Okay, so here it is. So I have the array. Now, the problem actually doesn't need long, but I decided to use long anyway. I guess I'll explain why. So there's the array, and the array actually has at most 100,000 entries, but I have 100,002. So what I'm going to do is I'm actually going to put everything from 1 to possibly n, and then in n+1, I'm going to put something else. So somehow this is the real array, and then I'm going to initialize these two somehow. Okay, so why do I do that? Because it makes my code a little bit easier in terms of I don't have to worry about special cases. So I'm going to initialize this to the minimum possible thing. So it's basically -infinity. And I use long min. That's the smallest possible long you can have. And over here, I basically use +infinity. Now, why do I use long? Because in the original problem, I guess in the original problem, it doesn't actually say. It just says that every entry is a distinct 32-bit signed integer. Okay, so any 32-bit signed integer is possible. So if I want to use an infinity, I need to use something that's bigger than a normal 32-bit integer. So I just switch to long. So then I know that this infinity definitely will be bigger or smaller than anything that's in my input. And then what I do next, I read it in. Right? So this is just reading it in. And then I have an array called leftmax. So my leftmax, so this got left. Basically, every entry would just be the maximum. So this is entry 2, would be the maximum of everything from here, from the beginning of this array to here. So the first entry would just, and I compute this always between 1 to n-1. Actually, I don't have to go to n-1, n+1, it doesn't matter. But I just only care about from 1 to n. And I always look at, if I want to know what is the maximum here, it's basically whatever the maximum is in the first two spots plus the maximum of this one. And the maximum first two spots is this one. So that's leftmax i-1, and then ai. And that will basically give me the current maximum. And the reason why I have sort of 2 extra elements on each end, it's because when I do this i-1, I wanted to make sure that I can always go backwards to i-1 and not run out of bounds. If I didn't have that, then I have to write a special case to start this off. And then right min, it's basically the same thing, except I run backwards. And basically the right min at I is the minimum of right min of i+1 and the elements in the array. So if I'm taking the minimum of whatever it is, then I'm taking the minimum of this and the minimum of everybody here, which I already computed with right min of i+1. Okay, so now basically at every point I know what is the maximum to the left of me and what is the minimum to the right of me. So I started counting, and then for each element, if the element is bigger than or equal to the max of the left side and less than the min of the right side, if both of these are true, then this evaluates to true, which also means gets translated to be the integer 1. And if it's false, it translates to integer 0. So I just add it into the sum, and then that just keeps the count. If you didn't like that, you can write an if statement, and then if this is true, then answer plus plus. Okay, so that's this problem. So the idea, I guess, is that you want to avoid doing quadratic work, right? Big O of n squared is hopeless for this problem. So then you have to say, okay, what am I really comparing? Right? I'm comparing, am I bigger than or equal to things on the left? Am I smaller than things on the right? And if you actually know the minimum or maximum of a appropriate chunk, you don't actually need to do the comparison for every element. So you just have to make sure that you update all of that as you go. Okay, does that make sense? Any questions? Comments? Okay, if not, then I'm going to move on to the next one. The next one is kind of messy. There's a lot of words. So the easiest thing to do is to show you the input output. There's only, okay. So the input basically start with a bunch of words, and basically this is a bunch of songs, and each song is identified a bunch of attributes, at most 20. Okay, so at most 20 attributes, and so at most 20 attribute here, and each attribute, they are basically only letters from uppercase, lowercase letters, 0 to 9, and underscore. So there's no space. And so you read in the attributes, so the artist, album, song title, length, seconds. So there are 4 attributes here. And then they tell you that there are 5 songs here. And each song will basically be 4 things, right? Artist, album, title, and then length in seconds. Okay, so that's the database of songs. And then they're going to give you 3 commands to sort things. So what do you want to sort? First, you want to sort everything by the artist. And then you want to sort by album, and then you want to sort by song title. But whenever you sort something, and if there's a tie, then you should preserve the order from the last step. Okay, so let's see. The first step, you sort by artist. So here, this is the output when you sort by artist. Okay, so you once again print the attributes, and then you sort things by artist. And if there's a tie, so here you have 3 songs that's a tie, then you want to keep the same order as the original. Okay, so it's the same order as the original. Okay, then what do you do next? Next step, you sort by album. So sorting by album, album is this one. So this is Dad Loves His Work first, and then Piano Favorites and Summer Lullaby. Oh, it's just Summer. That's the order. But then these 3 have a tie. So what order do you use? You use whatever the order it was before. Okay, from the previous step. And then finally, you sort by song title. So song title is this Hard Times, London Town Lullaby, and so on. And then here, is there anything that has ties or song title? I don't think so. So I guess with song title, we just sort it completely. So that's it. So it's just, I guess you just have to know how to sort. And in this problem, there are just even 100 songs. So you don't have to use anything fancy if you don't want. You can use whatever sorting. You can even use bubble sort if that's all you want. But of course, we don't really want to write sort, because the standard C++ library has sorts. So why do we write our own? So what to do, right? What to do? So I guess this is basically just a relatively simple thing, but it kind of exercise a little bit about your STL knowledge. Okay, so what you're going to have is some kind of a record. I guess if you want, let me switch back to the black pen here. So you have some kind of record struct, and then maybe you have I don't know what you call it, song, and then you have a bunch of stuff, string, attribute 1, and so on. But the problem is you don't know how many attributes there are. So the fact that you actually know how many, that everything is just a string, maybe it's easier just to use an array. So song would just be an array of string. Okay, and up to 20, let's say. You don't have to have all 20 fields because it might not have all 20 attributes. It might just have 4, for example. And then basically then each time they ask you to sort, you're going to be asked to use one of these as the key. You don't know which one, but you can do a search. One of these fields is going to be as a key, and then you sort them. So what do? Basically, you have a comparison function in C++ bool, and you have maybe constant. Well, okay, so this is a little bit tricky. Maybe it's easier if you use a vector, actually, because C++ array is not an object that can be easily moved around. So maybe we use a vector of string called song. Then your comparison operator would be basically like this. S1. And then now there's maybe a bit tricky because you don't know what the key is. So key would just be some maybe 0, 1, 2, basically an ID of the attributes, number of attribute minus 1. And then you have to say return S1 bracket key is less than S2 bracket key. So this will compare whatever key is pointing to. But where's key? Well, we will do what we're never supposed to do in any of our classes. Use a global variable. Okay. If you use a global variable that sets properly, then when you call this comparison function, then it will point to the right place and do the comparison, do the right comparison. If you really don't like this because you don't like this kind of global variable business, I will maybe say a little bit afterwards. Okay, now if you have a vector of song, so you have a vector string, it's a song. So if you have a list, let's say song list, what is the data type? It's going to be vector of string, because each song is a vector, and then you have a vector of them. And then you would say sort. So you'd set the key somehow before you do this as a global variable, and then you would say sort begin song list and song list. And then you say CMP using the special comparison operator, and that will sort your list, okay, by the key that you're supposed to sort it with. Okay. What's the problem? Why is this not going to work? What is it? Anybody notice any problem? So the problem says that if there's a tie between two entries, what are you supposed to do? Keep the original order. I know by original, I mean the original order before you execute sort. Okay, so if you have already changed your order in previous sorting steps, the output of the previous step is the original order. That's why I put the original in quotes. And here, if you use C++ sort, if you have two entries that have the same key, C++ can sort it in whichever way it feels like. And so that's not going to work. Now, does anybody know what kind of, if you have a sorting algorithm so that if two entries are tied, you don't change the relative order? Does anybody know, have anybody heard of a term for this kind of sorting? Have you seen this word before? To describe the property that if you have two entries that have the same key, you don't switch them around. So the name, the property of sorting algorithm is called stable. If whenever you have two entries that have the same key, you do not switch their order. Okay, some algorithms are not stable. Some algorithms are stable. So, quicksort may not be stable, but maybe other sort can be made stable. So if you just use sort, there's no guarantee. But in STL, it's actually really simple. You just add this, and STL will choose the algorithm that makes sure that things are stable. And so things that have the same keys will never get switched. So I guess this is just, whether you know that this function exists in the standard library. If you know that it exists in the library, then it's really not that bad, because you just have to call. If you didn't know that it exists in in here, then you can kind of fake it if you want. Okay, so how do you fake it? So whatever thing that you're trying to sort, you have a vector of X, doesn't really matter what it is, V, and you're trying to sort it. And imagine that you already have a comparison operator for X. Well, instead of doing a vector of X, you can do vector of pair of X and int V. So your elements would be a little bit fatter. So your indices would be here. This would be your things in X, whatever it is. And then you can attach to it in your second element, just the index of your array, like this. So when you sort, when you look at the comparison function for pair, it's going to compare by the first entry. And if there's a tie, it will compare by the second one. So if there's a tie, comparing by the second one means that if it's earlier in the original array, it will still be earlier. And this is a trick that you can fake stable sorting at the expense of basically making an extra field in your array before you sort. It's a little bit, it's not that hard to do, but it's more work, right? If you didn't have to do that, you don't do it. Okay, now let me show you the code, my solution, before I tell you what happens to those of you that are subscribing to the religion that you shall not use global variables. Okay, so here's my code. Okay, so I have a vector string that stores the attributes, and the song list is just a double vector, a vector of strings. And then, like I said, I have this global variable key. I have this comparison function, which is exactly what I showed you before. So let's, and then this prints, basically just print the attributes, and then for each song, print out all the fields. Okay, so this is just a printing function, it's not that interesting. Okay, so now what's going on here. The first thing is I need to read in the list of attributes, but the problem is I don't know how many attributes there are, right? So there could be a bunch of attributes. I know that at most 20, but I don't know that there might be 7 or whatever. So I can't just use cin like this and just loop it 7 times because I don't know it's 7. But I know that they all are in one line. So what I do is I read in a string. So now S is the string containing all the fields. And then in C++, you can turn the string into an input stream using something called iString stream. So now you have an input stream. It's kind of like somebody is typing the content of this string as you're reading input. And then we use the string stream almost the same way as cin. So we just keep on reading for another string until there's an end of file. End of file basically means the end of the string. So if there's 7 attributes, I will loop this 7 times, and every time I will read another one, I push it back into the list of attributes. Okay, so this is a little trick that if you have a bunch of things on one line and you don't know how many there are, the trick is to read it into a line, turn it into a string stream, and then pick it apart like this. Okay, so this is a trick that maybe you have not seen. Okay, then I read the number of songs. Then for each song, I would loop through the number of attributes and just keep reading. So this time I know exactly how many attributes there are, so I don't need to play this trick again. I can just do a loop and I read it, push it into the song. This vector V is the current song, and then I push it into the song list. So that's just dealing with the input. Okay. And then what's next? Oops. Okay, so what's next? So down here, this is where I do everything. So I read in the number of sorting commands. Okay, so here, and then for each one, for each sorting command, I read the attribute that you're trying to sort. And then this is a STL command that basically look into my attribute array, actually attribute vector, and see what is the index. So which entry match the attribute that I just read. Okay, so that's what give me 0, 1, 2, and so on. This will be the index. Now, normally I should also check if the attribute is not found, but I guess I'm not going to worry about that, because in this problem you're not going to get bad inputs. And then I just call sort. Well, remember to call stable sort actually. And then I print it, and that's the end. And I just do it n times, 1 for every single command, sorting command. Okay. Any questions about this? No, I don't know how many of you are religiously against global variables. I'm not, I use them all the time. But if you are, how do you find a way to pass this key? Okay, how do you find a way to pass this key into this comparison function when you are not the one calling the function, right? So what I mean, because you are passing the function into sort. Stable sort, or whatever sort you're using, STL, the STL routine is the one that's calling it. The STL, we expect whatever function you pass in takes exactly 2 parameters, not 3. So you can't just put another parameter here that says I want to pass in key. Okay. So does anybody know, I guess, the proper C++ way of passing the key into this function and not use global variable? Has anybody learned this at all? Yes, no?
I'm guessing it's not just making it a parameter, since you just said that.
Yeah, you can't, because if you make it 3 parameter, you can't compile this code here. This code says it will say that the comparison function that you sent makes no sense because it's expecting 2 parameters.
Can you make an object and call it?
Aha, right. So the trick is that you would make a class, let's call it comparator, just I don't know, whatever you want to call it. And then one of your private variables could be a key. And then in your public, you'll have a bool operator round bracket, and then with the 2 parameters. And then the code would be exactly the same. Okay, my braces are badly lined up here. The code would be exactly the code that I had before. And then in the constructor of this class, you would initialize this here like this. And then down here, you would say CMP key. And that will construct an object. And when it constructs this object, it will store in the object the key, so that when it's operating, I guess I should put const down here. So when it's operating, it has access to this variable, which is not exactly global, but it's sort of limited in scope inside this object. So that's the proper way of doing it. It's what is called function object. And well, anyway, that's the proper way. But in a programming context, I don't want to write this much stuff to do it properly, so I just use a global variable. Nobody's going to complain because you want to get it done quickly. You're not looking for the most proper code. If you're looking for the most proper code, you'll never look in programming context code. Okay, anyway, that's a side issue. Any questions? All right. Death Star. Okay, now there's a very strange backstory. It doesn't really matter what the backstory is. I think the easiest thing to do is to show you what the problem is. Just explain. You have a bunch of numbers, A1, A2, up to AN. These are integers, and they are non-negative, so it's greater than or equal to 0, and at most 1 billion. Okay, so you have these integers, but they are unknown. You don't know what they are. You have to figure them out. Okay, you have to figure out what the numbers are. What do they give you? What they're going to give you is AI and AJ for all I and J that are not the same. And this N is a bitwise N. Okay, so for example, if I know that this is, I don't know, 5 and this is 3, well, 5 is 101, so this is 5 in decimal binary is 101. 3 is 011, so when you do a bitwise AND, it's 001. Okay, so that's what they're going to give you is this array. And how do you read it? The matrix entry at row I, column J is AI and AJ. So here it's saying that this entry says that if you take A0, oh, sorry, I'm using 1, A1 and bitwise AND with A2, the answer is 1. And similarly, A1 bitwise AND with 3, the answer is 1. The diagonal are always 0 because the diagonals don't mean anything. Because if they tell you what the diagonals are, if they tell you what is AI and AI, then they might as well just tell you the answer because that's That's the answer if they actually give this to you. Okay, so you have to come up with a set of values, AEIs, so that when you do the pairwise, bitwise AND, it will come out exactly like what they give you. And the only thing, so one of the things that you have to also know, if they even tell you that, the answer doesn't need to be unique. So there might be multiple solutions. It doesn't matter which one you give. It says the output must contain any array of n non-negative integers at most 10 to the 9 that meet the requirement. So anything that, so even if there are multiple solutions, you can give me any one as long as the pairwise bitwise AND is what you're supposed to get. That's fine. Okay. You don't have to make sure that everything you find that's smallest or biggest or whatever. Okay, so this first example, they're basically saying when you take the bitwise AND of any pair, the answer is always 1. So one possible solution is 1, 1, 1. Okay, when you bitwise AND with any two of them, it's always 1. Okay, this one is a little bit trickier, right? If you say 1 bitwise AND with the second one, it's 0. Bitwise AND with 3, 4, and 5 are all 1. So if you try bitwise AND 1 with 2 is 0, because this is 0, 0, 1, this is 0, 1, 0, 0, 1, 1, 0, 0, 1, and 11 is 1, 0, 1, 1. So actually there are 4 bits here, so I'm going to put 4 bits. So when for example, let's look at this. This is the third one bitwise, or with, let's say, third one with fifth one. It's 3, so I look at this one, bitwise AND with this one, and sure enough, the only positions where they both have a 1 is the last 2 positions, and that's 3. Okay, so you're given this, and you have to figure out this. And the array, the number of elements is at most 1,000. So 1,000 means that n squared is okay. So think of n squared, it's when n is about 1,000, n squared is about 1,000,000, and 1,000,000 is no problem at all. And the other reason why n squared is okay, it's because the input that they give you is already n squared. Just reading the input will take the n squared time, even if you don't do anything else. So there's really not much you can do other than n squared, or maybe you have to do at least n squared just to read the input. Okay. All right. So what should we do? What should we do? So we see, for example, let's look at this one. Right. This one is A3 bitwise and A5. And I'll just write it in binary. It's this. What does that say? What does that tell you about A3 and A5? What does that tell you?
It's saying their binary adds up to 3.
Not add up. Okay, this is an AND. So A3, let's write it this way. So A3 is 4 bits and A5 is 4 bits. What do you know about the bits in A3 and A5? Are they all unknown, or do you know something? Is there anything that you know about the bits that are in A3 and A5? How can you get a 1 at the end? When you do a bitwise AND, how can you get a 1?
You have to have a 1 and a 1.
The only way you can get a 1 is 1 and 1. There's no other way you can get 1. So when you see a 1 in this position, you know immediately that A3 and A5 must have a 1 in those positions. Okay? And similarly, you know that A3 and A5 must have a 1 in this position too. Now, you don't know these two positions. The only thing that you know is that both of them cannot be, so you cannot have in this position, the first position, if one of them is 1, the other one must be 0. They cannot both be 1, but they can also both be 0. Okay, you don't know which one yet. Okay, so that's what you know. You okay with that? Everybody okay with that? Okay, so what other things do we know? Right, A3, this is A2 and A3. So A2 and A3, it's 2. So this is 2. So what does that tell you? That tells you that the second bit from the left, sorry, second bit from the right is 1. You don't know anything else other than that they cannot both be 1. So what are we going to do? Right, so for example, the only thing that you have to worry about here, you can set them to anything except that you cannot set them both once. Now, knowing that A3 from some other way, it's already 1, then you know that this has to be 0. Okay, but it's a little bit, I mean, you can do this, keeping track of this and looking back and forth and say, well, this is 1 now from some other entry, so this has to be 0. But it's, in fact, we can just set, it's easier if you just assume that everything is 0 unless otherwise you found out evidence against it. And the only evidence you find it against it is basically when you see a number that's non-zero in this entry, you basically turn on the particular bit. And at the end, it turns out that that's all you have to do. Because what happened is that you're going to look at these entries. This one says that A1, so let's look at this, A1, A3, A4, A5. Each one has 4 bits. So A1 and A3, the last bit are on, so A1 and A3, A1 and A4, A1 and A5. Okay, so I fill that out. So this takes care of this row. The next row, A2 and A3, A2 and A3 both have this bit on. A2 and A5 both have this bit on. Then here, I actually don't have to look at anything that's to the left of the diagonal because the whole matrix is symmetric anyway. I only have to look this way. So 3 and 4 both have the last bit on. It's already on. Doesn't hurt to turn them on again. And 3 and 4, the 3 and 5 both have the last 2 bits on. Well, it's already on. Okay, so this is done. Then finally, this bit, 4 and 5, the last bit is on. So that both of them have to be turned on, and that's it. So my answer would be 1. So everything else I'll pretend to be 0. So this would be 2, 3, 1, 3. Now this answer is different from this one. Okay, but it actually still works. Why? Because 11 is actually 8 plus 3, so they basically just add a 1 here. And when you have a single 1 here, and it with anything else, it basically wipes it out. So it doesn't actually matter. But you can, if you don't know, if you don't have any evidence that it's a 1, you can always assume that it's 0. And it turns out that that's all you have to do. Does that make sense? Now, I guess the code, it's relatively short, but I guess it involves whether you know how well you know, how do I put it, binary bitwise operations. So what am I going to do? Well, so okay, I have this array A, which is my unknown integers that I'm trying to figure out. At the beginning, I assume that they're all zeros. Every bit is 0. I read in AND, then I go through the array. So I actually loop through the entire array because I have to read them anyway. So this is I and this is J. And then I read in the entry, whatever this might be. So let's say 3. So I read in the entry, if I is equals to J, I just skip it. But make sure I skip it only after I read the number. Because if I don't read the number, then this will just be in the input. I don't know, I'll just be screwed up because I'll be out of sync. I have to make, even though I don't want to do anything with it, I still have to read it. Okay, and then here's the I guess here's the trick, if you want to call it. So whatever this is, let's make it a little bit more interesting. Let's say it's 10. So 10 in binary is 1010. What do I want to do with A? And this is I and J. So what do I want to do with AI and AJ? Well, whatever binary pattern, I want to go and turn this bit on and turn this bit on. Whatever I have in I and J already, I want to turn these 2 bits on. So how do I do that? I use a bitwise OR operator. So if I take something, a number, with a vertical bar followed by a number like this, then I am using this number, so this one here, as a bit pattern, and whatever it's 1 here, I will go into X and turn that bit on. Okay, so an OR is to turn things on. And then they basically turned it on based on the mask and then assigned it back to AI. And this is a very simple way of doing it. I don't have to actually pick the bits apart. I can actually do it all in one go with bitwise operations. And then basically after I've done all this, the values in the array A are exactly what I want. So I just print it out. And that's the end of the problem. Okay. Any questions?
What is the difference between binary addition and bitwise AND?
Oh, okay. So, so let's say, give me 2 numbers, any 2 numbers. You want to give me 2 numbers to try?
2 and 5. Sorry, I was muted.
Okay, 2 and 5. Okay, so 2 is this, and oh, actually, this one. Okay, maybe this is not the best. Okay, we'll do it anyway. So 2 plus 5, of course, we all know it's 7. And when you do binary, because this time there's no carries, it's just 1, 1, 1. Now, what other things can you do? If you do 2 and 5 as a binary, bitwise AND, every single position, there are no 2 1s here, so they just get 0. But if you do 2 or 5 bitwise AND, it's actually the same thing as 7, because in this case everything has exactly 1 1. Every column has 1 0 and 1 1. Okay, now let's try a different number. So let's try. Let's see, what do I try? Let's say I try 1 and 5. Okay, 1 plus 5. And of course, we know that 1 plus 5 is 6. 1 is like this, 5 is like this. And now when you add it, this becomes 0, and there's a carry to the next one, right? If you're doing 1 and 5, 0, 0, 1, 1, 0, 1, it will just be this, and it'll be 1. If you do 1 or 5, this is the binary bitwise OR, it will actually just be 5. The 1 just gets absorbed. Okay,
That makes sense.
So bitwise AND, you just bitwise whatever, bitwise AND, bitwise OR, bitwise exclusive OR, it doesn't really matter what it is, but whenever you say bitwise, you're looking at every single bit individually. There's never any influence from one bit to the next. Whereas in here, right, 0 plus 0, what the answer is actually depends on what comes before that column, right? Because whether there's a carry or not. So that's the difference between normal integer arithmetic and bitwise computation.
Thank you.
Do you talk about, I don't know if you've taken 2610, maybe you talk about that.
I'm in it and I should know that, but I wasn't like picturing it that way because I'm used to looking at it in diagrams, not
Oh,
like
okay.
lining it up like addition. So I was
Oh,
a
I
little
see.
confused what was going on.
Yeah, so how is 2610 being done right now? I mean, it used to be that you actually build this physical circuit with wires and you actually maybe at least mentally see where the bits are.
We
But,
use Logisim now. It's an application that has like you can make the logic diagrams, but then Trent and Nicole have added like all of the chips and everything too.
okay, so you
And
do
they
simulation.
made yeah, and they made like a virtual breadboard and stuff because people weren't like seeing how it was actually supposed to be set up. They were getting some weird circuits, so they
Right,
made that for us too. But I think
right.
it works pretty well. I guess I
Yeah.
wouldn't know because I haven't done it in person, but
Yeah, it's not the same. It's not the
no,
same when you don't build the thing. But anyway,
yeah.
okay. So anyway, that's the difference between bitwise and arithmetic. There's also so maybe actually this is a good digression. So there are basically 4 different type of bitwise operators. There's, well, yes, you can guess. There's not, there's and there's or. So why do I say there are 4? Because there's some exclusive or, at least in C++. So how do you do things bitwise? So if you have a number, let's say integer m, whatever that is, and integer, there'll be a binary pattern of some sort. If you want to negate every single bit, it's tilde m. So we'll flip the zeros to ones and ones to zeros. And it's a and b. I guess I should use m. Whatever. You know what I mean? Or is vertical bar. An exclusive or, it's the het. And this is a common first year 1620 mistake because, at some point you might want to say, I don't know, 4 raised to the power 2 or something like that, and they'll write 4 het 2, and then they'll get completely confused by the results because it is not, has nothing to do with exponentiation, but rather it's an exclusive or. Now, technically, people that are watching this video, I couldn't erase it fast enough because what I said is actually wrong. You should, if you really, really, truly want to do bitwise operations, you should use unsigned integers. So if you are, I guess if you're in 2610, you might know that unsigned integers, how is it represented? Well, it's just sort of the base 2 representation. Whatever you think base 2 representation is, right? It's all the digits times the appropriate powers of 2 added together. Okay. But what is sign? Sign is 2's complement. And 2's complement, one of the problem is with negative numbers, the first bit is a sort of a sign bit. And when you try to do bit operations with signed integers, strange things may happen to the sign bit. You can actually read the exact behavior in the C++ standards if you wish to read some kind of a legal document on exactly what a compiler is supposed to do. But chances are it's not doing what you think it should be doing relative to the basic logical operations and or nots and exclusive or. So the best thing to do is just use unsigned. Or if you know, for example, if you use int and 32-bit and you know that you're never going to use you're never going to need to use that last bit, then it's okay too. And so in this problem, why am I allowed to do this with int? Because they told me that everything is at most a billion. So billion, it's right. So a 31-bit integer, a 32-bit signed integer, it's up to 2 billion. So up to 1 billion, you don't even need to get that high. You're never going to touch that signed bit. So that's why I know it's safe. But if you're not sure, use unsigned. Okay, so now what are the things that we can do? Not, and, or, and exclusive or. So what is the purpose of these? Well, not is just negate. And is often used to test a particular bit or turn off a bit. So if I want to know if a certain bit is on, what I would do is I would say A and 1 like this. Okay, so what's going on? This is what is called a left shift operator. It's going to produce a number that is zeros everywhere except a 1 in the middle, and the middle is the ith position. Okay, so this is going to be a number that has exactly 1 ones in the binary representation. And when you do a bitwise AND, the zeros basically means that nothing else matters except for this one. And then, so if you look at A, there'll be a bunch of stuff you don't actually care because everywhere is 0. So when you do the AND, it's 0. But right above 1, when you do the 1 and this question mark, if this question mark is 0, of course it's 0. But if this question mark is 1, then you get a non-zero. So this test, if it comes back as non-zero, it means that the ith bit of A is on. If it comes back as 0, it means the ith bit is off. Now, how do you turn off a bit? To turn off a bit, what you want to do is let me erase it. When you do an AND, basically, if you see a 1 basically just copies whatever this is when you do an AND. And when you see a 0, when you do an AND, it wipes it out. It turns it off. So basically, if you want to turn off the ith bit, you want to AND it with something like this. So how do I get something like this? It's basically this, and then flip it. Okay, and that will give you turning off a bit. Or is for usually turning on a bit. So it's just this. If you want to turn on a specific bit, if you want to turn off a bunch at a time, like for example here, you can turn off a whole thing, more than 1 bit at a time. And then exclusive OR is usually used to toggle. So if it's an on, it becomes off. If it's off, it becomes an on. So how do you toggle? You do something like this. That will toggle the ith bit. Okay, so this is sort of bit operations that may be useful in different scenarios. So C++ is good in the sense that you have easy access to these low-level operations. In some other language, maybe it's hard to actually access these operations. Anyway, so that's a bit of a digression, but it could be useful at some point. Okay, so that's that. So what the heck am I doing? I said that there's some kind of a theme. Maybe, I don't know if people think that there's any kind of a theme, right? So what's going on? I have a pivot, which kind of figures out whether something is to the left. To the left is bigger than, less than me, and to the right is bigger than me. There's a sorting thing. There's this other one that plays with bits. And then I haven't talked about these other two yet. So basically, I guess, my theme this week, it's sort of STL plus, I guess, simple data manipulation. By simple, I mean basic types, like, integers, right? I'm not talking about some complicated type like strings or other things. Right? So that's my theme this week. It's some of the things that you know, recognizing things that are already in the standard template library, so you don't have to reinvent the wheel, and some simple data manipulation. Okay, so now that I have revealed the theme of this week, let's look at the next one. Okay, since we're talking about 2610, here's 2610. You have some combinational circuits. You have some digital gates. You have the input A, B, C, D. You have things that combines with and, or, and not. And then they even tell you, so star is basically and, plus is basically or, and then minus is basically not. And then they're going to give things to you in what is called postfix notation. So the syntax is an uppercase letter A through Z. It's a valid circuit. So basically a letter by itself is a valid circuit. In other words, the input alone without any gates is a valid circuit. And what is the output? Well, it's exactly what the input value is. If you have two valid circuits, you can combine them by sticking them one after the other, followed by a star. That means that it's a valid circuit that produces the AND of the outputs of C1 and C2. Plus is similar for OR, and then minus is the similar for not. So for example, if they write AB star CD plus minus plus, what does that mean? It means that AB times, that's one subcircuit, which is the result of A and B. CD plus is another subcircuit. Then the minus refers to the subcircuit. That's the, oops, sorry, no, I got it wrong. Because minus is a single thing, it's just a not. So the minus response correspond to this part is the negation of CD plus, and then the plus needs two things. It's the plus of these two circuits. So this is sometimes called a postfix. Why am I writing this when it's already here? Postfix notation. Have you seen this? Has anybody seen postfix notation in any class?
Think so, and we use a stack, right?
Exactly. So this is like one of the standard things that everybody hopefully should know after some kind of computer science education. And the idea is that you basically just read from left to right. And as you see things, if you see just an input, you push it on the stack. So I'm just going to draw my stack sort of this way, with this way being the top and this way being the bottom. So I push A, then I push B, and then when I see an operator, I say, okay, I need two things. So I take two things off the stack, apply the operation, and then put the result back in. So the result back in would be, I call it result 1. Then I see C and D, so I push C and D in. Then I see a plus, so I take two things off the top of the stack, combine, and I get what's called result 2. Then I see another one. This time, this other one needs only one parameter, so I pop the top thing in, so pop the top thing out, and put the result in. Let's call it result 3. And then finally, when I see a plus, I take the last two things on the top of the stack and then combine them, push it in, and then at the end, there should be exactly one thing on the stack, and that's the answer. Now, in this problem, I believe that they guarantee that everything is valid. Okay, so how do they give the input to you? Maybe it's easier, so just to read it. They tell you that there are 4 variables, and the variables are a letter from A to Z, I guess, but so they say that each circuit is always valid and uses only the first n letters of the alphabet. So if it's 4, it's always A, B, C, D. Okay, and then basically they tell you that these are true these are the values of A, B, C, and D, true, false, and then this is the expression. So I guess the main thing is you need to know that you use a stack, and then you just have to learn how to use the STL stack. So is there anybody that have not seen this stack evaluation algorithm that evaluates the postfix expression by pushing operands into a stack and then popping things up to do operation? Everybody has seen this? Okay, so there's hopefully nothing for me to explain other than maybe how to write it in C++. So here it is. So I have a Boolean array that stores the value of the 26 variables. Now, why do I use 256? Okay, we'll go on and look at it. So what did I first do? I read in the number of variables. For each variable, I read in the character which is either true or false. And then C equals T is either going to be true or false. So basically, I'm turning the letter T and F into an actual Boolean value. And then I'm assigning it to the letter capital A plus 0, 1, 2, and so on. So what am I doing? I am actually using into this indexing the ASCII value of the letters A, B, C, and so on. Okay, so I'm not actually indexing things from 0 to 25 like, I don't know, a normal person would do, maybe. Maybe you think that you should use 0 to 25, it's easier. I'm actually using the letters. And because letters, they're 8-bit letters, so if I use 256, I'm safe. Actually, I can use 128, it's safe because the values from bigger than 127 are what they call extended ASCII code, and it will never be one of these standard characters. Okay, I will write pop quiz question that I'll come back to later. Okay. Now, what am I going to do? I have a stack of Boolean because that's going to store my results. And then for every single, basically I just keep reading characters in my postfix expression. If it's an uppercase letter, then I push the value of that letter. Now, because I use the character as my index of my Boolean value array, I don't have to translate that back to 0 to 250, 0 to 25. So I guess you can say that either you translate here at the beginning or you translate here when you look it up. I chose to translate at the beginning, not at the time I look it up. Right? If I decide to use value from 0 to 25, then here I would have to do C minus capital A. Okay? It doesn't really matter which way you do it, it's all equivalent. Okay, I just decided to do it this way. I don't know why, but that's just the way I did it. And then what? Okay, so if it's a star, okay, if it's a star, then I take the top 2 elements from the stack, and in C++, in all the data structures, whether it's stack or queue or other things, looking at something does not actually get rid of it. So looking and taking it away are 2 separate operations. So this, you look at the top, and this, you pop the top. You must remember to do both. Okay. There are other languages where just the fact of looking, remove it. Okay. But in the C++, in the standard template library, looking and popping are 2 different operations. So you must remember to do both of them. Okay. So now I did not bother to check if the stack is empty because they told me that everything is a valid expression. But in general, it's better that I make sure that the stack is not empty before I pop, okay, before I even look. Okay, and then so I look at the top 2, pop them, and then what do? If it's a star, I combine them with an AND, Now, why do I use a 1? What is the difference between this and this? This is a bitwise and this is a logical and, which in most cases are actually exactly the same. Why? Because in C++, it's guaranteed that false is 0 and true is 1. So if you're using only Boolean values and you're only ever computing things that comes, all the Boolean values that you put are always coming out of Boolean expressions in C++, then this is true, it's 1, false is 0, and bitwise and logical operations are exactly the same. However, in C++, you don't need to use Boolean. When you mean Boolean, you can use any integer values. So if you want, you can put in, I don't know, I can say if C is equals to T, then value is equals to, I don't know, 123. Else value is equal to 0. That is also legal C++ because any number that is non-zero is interpreted as true. And if that's the case, if I use numbers like these, then bitwise and logical are different. Okay, so I guess if you're not sure, use logical when the problem asks for logical things. Use bitwise if the problem asks for bitwise things. Yeah, so in C++, basically any non-zero value is considered to be true, but the only false value is 0. So in fact, I'll show you a piece of code that I've seen many people write, and I hope you don't write this. So you have some tests. You do some tests, and you write equals true. Then do something. And you might say, well, yeah, this reads very well because if this is true, do this. Or maybe you write similar things. If this test is equals to false, do something, right? One of these two. And it turns out that this is safe and this is no good because the true, when you use a constant true, it's always going to be 1. And false is always going to be 0. There's only one way to say false, and that's 0. So this test is safe. But this test, if this is not something that you wrote, if somebody else wrote it, what if it returns, I don't know, 57 to mean it's true? And now all of a sudden you get screwed because 57 is not the same as 1. And so you think that the whole thing is false. So just remember in C++, just like in real life, there are many, many versions of truth. So you have to remember that don't test for only one version of truth. Test for all of them. Okay. So what's next? The rest of it is pretty much the same. If it's a plus, I do exactly the same thing, except this time I push the or. And then if it's a not, so then I only take one thing, not two, and I push the negation. So the exclamation mark, of course, is a logical not instead of the tilde, which is a bitwise. Now, not, it's actually really important that you don't use bitwise because if it's true, it's 1. But what is 1? 1 is this. So if I take tilde true, this is going to turn into 1, 1, 1, 1, 1, 1, 0, which is still true. Okay, because this is non-zero. So when you do not, the tilde and the exclamation marks are definitely different. Do not mix them up. Okay. And then finally, if you've done everything right and if the expression is valid, when you actually finish, the stack should have exactly one thing. So I just looked up whatever is on the top of the stack, which is the only thing that should be on the stack. And if and then I look at the Boolean value. If it's true, I print T, otherwise I print F. Okay, so the algorithm itself should not be that much of a challenge. You should know this algorithm, but how you implement it in C++ quickly, I guess that's to make, again, you have to know how to use the stack and so on. Now, okay, what is this pop quiz? Before I go into a pop quiz, let me ask, are there any questions or comments before I go on?
So when you said not to compare if it's equal to true, in that
Yeah.
case, if it was equal to 57, you would just have to like scan through their code and see where they set it to 57 and then
No, okay,
just
no, but you might not, if you're using somebody else's library,
yeah.
you don't have a choice. You might not be able to scan through the code. I mean, you might say, well, what the heck? Why did they use 57 or whatever it is? Okay, but you can't, you don't know. Okay, now, if instead of saying if test blah, blah, blah equals true, don't say that. Just say this. That's enough.
Okay.
And automatically C++ would just take whatever it comes back from this and interpret it as non-zero true, 0 false.
Okay, that makes sense.
And in fact, most people would not even write this, right? If you write this, you write this instead. Okay. But anyway, you can say that these are bad style, but in fact, this is okay and this is just wrong. And you have to know why it's wrong. Now, it's true that most functions that are written in by sane people would return Boolean true or false, but you cannot absolutely guarantee that. Okay, basically, when you use other people's code, you always have to pretend that everybody else is a possible lunatic that only write to the specs. Okay, pop quiz. Okay, what is this pop quiz? What am I doing here? I have a character. Then I take this character and you take this character and index it with this array. Yeah. Pop quiz. If I tell you that, so I told you the characters are just integers. What is the range of numbers I'm allowed to put into a character without overflow? How many bits do you think a character has? Anybody?
Is it 8 bits?
8 bits. Okay. So in C++ standards, a character is always 8 bits. There is no guarantee that integer is always 32 bits or long is 64 bits. But characters is always 8 bits. That's guaranteed in C++ standard. Okay, so now back to my original question. What is the range of integers? What are the maximum and minimum integer value I can store in this variable C? Eight bits. How many possible values are there? 2 to the 8, which is 256. So what are the values I can put in there in this character C? Anybody wants to tell me? Anybody have a guess? Is anybody too scared of what I might say to them?
I was just gonna say any of the ASCII characters, but I didn't know if that's what you're going for.
Okay, no, but the character is an integer value. So
yeah.
So that I can put numbers into this character, into this C. I can assign C equals to, I don't know, 16. Okay. So what numbers can I put into the C so that I don't get overflow? right? I now know that I can only put 256 different things in there. If I try to put 257 things, at least two of them will be colliding. There's some kind of overflow. So which 256 numbers can I put in there? Okay, maybe I ask you the same question. Int, let's say that it's 32-bit integers. 32-bit integers. Oops. What are the numbers I can put? Well, you hopefully know that the smallest 2 to the 32-bit is negative 2 to the 31, all the way to positive 2 to the 31 minus 1. And this is about 2.147 billion, roughly. So that's let's get rid of this arrow. So for 32-bit integers, the range of numbers you can put is this relatively big range. So for characters, what numbers can you store in there?
I'm gonna say negative 2 to the 7 to 2 to the 7 minus 1.
Okay, so let me just to make it even simpler, it's you're saying minus 128 to 127. Okay, anybody else have a guess? So another guess that's common, it's 0 to 255. What is the difference? Here with int, right, when you have int, you allow both positive and negative, and then if you say unsigned int, then it's only from 0 to 2 to the 32 minus 1. You cannot have negative. So if I were to write signed character, then this is the right range. If I were to say unsigned character, then this is the right range. And if I were here, I can also say signed int and unsigned int. So signed is a proper word that in C++ you can actually specifically say whether you want signed or unsigned numbers. And when you don't say anything, what do you get? Right, I didn't say anything. Normally people don't bother writing signed int. What do you get? You get the signed version. So here I did not write signed car. I did not write unsigned car. So most sane people, I suppose, would say that of course you meant signed. But you're wrong. And then once I said that, then you would say, now you mean unsigned car, but you're also wrong. The correct answer is, I don't know.
Always.
I feel like that question was a setup.
It's definitely a setup.
I think you mentioned that like a couple times in the 2 courses I took with you. So I'm like, I'll just not attempt to answer the question because I know I'll be wrong.
So the answer is that I don't know. And in fact, I don't know is the correct answer because in C++ standard, it says that it can be either one of these two, and it's whatever the compiler, it's what they call in the C++ standard, it's quite often you see the word implementation defined, meaning that the system that you're using, whether it's a compiler or the machine, can choose either one of these as the default. And you might say, what the hell? Why would you have a C++ standard that tells you that the standard is to choose one of many options? What kind of standard is that? So the issue is basically, it turns out that on some machines, and this is actually a CPU issue, it matches, what exactly does the CPU have instructions for dealing with characters? And it turns out that in some CPUs, it prefers, the character instructions prefer to work on this range. And on some CPUs, it prefers to work on this range. I actually don't remember which one is which, but I remember one thing for sure is that the Intel chips and the Mac chips are in the different end of the spectrum. One of them use one way and the other one use the other way. And so every once in a while, I'll have a student that say that the code works perfectly fine on their system, which is probably Mac. And then when they upload it to a machine at school, which uses Intel, everything breaks. Oh, actually, they didn't even know it breaks, but sometimes it breaks. Why does it break? Maybe they were using, let's say they were using this one, but then they have indices that are, you know, plus, let's say 200. But then when they use it on the other machine, the 200 becomes a negative value. Then you try to access the array at negative index. And guess what happens? The program crashes. So if you really, really care about which way you want, you have to write unsigned character and character. The good thing is that for most standard characters, especially the printable ones like A to Z, the English letters, the digits, and so on, this normal ASCII code, it always sits between 0 to 127. And so as long as you're using standard characters, I guess, either way you will be okay. You will always be in the right range. But if you use something, sometimes they call it extended ASCII, then you end up with 128 and above. And then depending on which system you're using, you might get all screwed up. All right, so this is one of these tidbits in C++ that many people don't know. And, you know, for those of you that ever, you know, want to impress your future boss at job interviews and they give you questions like this at your interview, right? Now you know the answer. There are lots of, there are a few other things in C++ that implementation define. And sometimes it kind of makes people, surprises people what the correct answer is. Anyway, that's a big detour, but still useful because for programming contests, I guess the thing is now at least you have Caddis, probably runs on Linux, on PC. If you're using Mac, right, you might be writing code that on your machine seems to work very well, and then you submit it and always crashes, maybe even crashes even on the sample inputs, and you'll be wondering what the heck is happening. It could be one of these implementation defined issues. Okay, so that's a huge sidetrack. Okay, the last one. Okay, so you have a programming language called BAPC. It's a language for working with lists of integers. Language has two built-in functions, reverse or drop. The function R reverses the input list, and D drops the first elements of its input and returns the rest, or gives an error in case its input is an empty list. To get more advanced behavior, the functions can be composed. AD is a function that applies first applies A to its input and then B to the resulting list. For example, RDD means that you reverse the list and then drop the first two elements. Unfortunately, our BAPC interpreter is a bit routed, so we ask you to write a new one. Given a BAPC program as input, return its output or error in case D is ever applied to an empty list. Lists are represented as the character, square bracket followed by a comma separated list of integers followed by a closing bracket. Notice that the input and output list can be quite long. Okay, so first line of inputs, it's one positive number, which is the number of test cases, at most 100. For each test case, you have a string T, which is up to 100,000 operations consisting of R and D. You have N, again, up to 100,000, which is the number of elements in the inputs. And one line with a list of N integers in the form of square bracket followed by a bunch of numbers separated by commas. Every number is between 1 and 100. So for each case, either print the resulting list or error. Okay, so let's look at the first one. Okay, so RDD, the answer is, you have 4 in the input. These are the 4 things. So R, you reverse it, so it becomes, so when you reverse it, becomes 4, 3, 2, 1. And then you drop, and then you drop. So the answer is the list containing 2 and 1. Okay, so 2 and 1. Next one. This is really easy. You have a list of with one thing. You call drop twice. So you drop the first time, gone. Call the second drop, error. Okay, so far, so good. And then the next one, it's RRD. So this is a list of 6 things you reverse. So reverse. But of course, if you're smarter than me, you realize that when you do a reverse followed by reverse, you just get the thing back. So you actually didn't have to do anything. And then you drop, and that's the answer. And then here, the last one, well, I guess it's pretty simple. You try to drop something that is empty, so of course you get an error. So that's the problem. What to do? So what to do? You need something. You need an array or some kind of data structure that allows you to store things. That pause layer that allows you to reverse and drop the first one quickly. Okay. Of course, if you use an array or even a vector, reversing is going to be a nightmare because reversing requires you to swap all the elements with its with the counterparts on the other side, right? If you have to do this, just reversing will take forever, right? Reversing, if you do it this way, will take linear time, so up to 100,000, and if you have to do this 100,000 times, that would be way too slow. That would be n squared, where n is 100,000. So what to do? Any ideas? So this is clearly, I guess, a data structure problem because they tell you what operations, you have a set of data, they tell you what operations you're supposed to do. And the good thing, I suppose, is that you don't have to worry about adding elements. This array, or container, I guess you can call it, things can only be removed. You can never add things. Okay. So what to do? Well, the first thing to realize is that you don't need to reverse. Why do I say that? If you keep track of, let's say, the begin and end, and let's say you know that beginning and end goes this way, if you ever reverse, instead of actually reversing anything, you can actually just swap the beginning and end. Whoop, I said swap. And begin, and then switch the arrow to point the other way. And so if you implement reverse this way, reverse is very easy to do. It's just a constant time operation. I just swap the begin and end, and then remember change the direction, whether you're going left to right, right to left. And if you do that, then drop basically means that you either drop something at this end or you drop something at the other end. So you need a data structure that allows you to drop something quickly at either end. And in C++, in the standard template library, what you want, it's a double-ended queue, or DEQ. So if you have a double-ended queue called queue, this actually allows you to index from Q0. You can index things like this all the way to the end. And there's also this Q.POP_FRONT and Q.POP_END. Pop back, sorry. Pop_back. So basically, if you keep track of which way is beginning and which way is end, right, which direction you're in, then when you see a drop, either you pop the front or you pop the back, depending on which direction you're facing. So you initialize the back with this. You either pop the front or pop the back. And then when you're done, when you process everything and you still haven't have an error, then either you print all the elements from this way, or you print all the elements from the other way, depending on which way you're facing. Right? You just have to remember how many R's you have seen before. And that's actually it. So you can actually use a queue, a double-ended queue, to do this. Now, let me erase all this mess. Okay, so there's a little bit of messiness because the input comes like, you have square bracket and then comma, 4, comma, 5, and close square bracket. So there's some things like here that reads a character and then don't use it, basically to get rid of the first and last open bracket, and then you read an integer, and then you have to read another character which eats the commas, but only eats the comma if it's not the last one. Anyway, there's some kind of messiness, but the whole point is you read the string, you read the number of elements, you read each element, and you push it into the queue. Okay? That's really the most important part. And then here, okay, so basically for each command, if I have a flag that remembers whether I reverse or not. If you tell me to reverse, then I just flipped it. Otherwise, it better be a drop. So actually, you don't even need the else if. You can just say else, but I guess this makes sure that you don't have a strange character somehow. And then if you try to drop and the size is 0, that means there's an error. Otherwise, you figure out which way you're facing. If you're reversed, then dropping the front is actually dropping the back. Otherwise, drop the front. And then at the end, if you were reversed, I just reverse it once at the end, and then I print the answer if I don't have an error. So if you know your STL well, then this is not too bad. Now, it turns out that I guess I have a different solution which doesn't have to require any complicated data structure. And the idea is that I actually don't even bother removing anything. So I actually just have a standard ordinary array of integers. And then I have a start, an end pointer, and then I have a direction, which is either +1 or -1. If I see an R, I would flip the direction, but also swap start and end if I see an R. And then if I see a drop, I basically take start and move it in the direction indicated by this. So if start is here and I want to drop this, then all I do is I move start to point to the next element, like this. And then if I drop again, I would just move it forward. So in fact, if I just use the pointers to say which way is front and back, where's the start of the array and where's the end of the array, I don't even need to actually physically drop anything. And then all I do at the end is just basically loop from start to end, whether it's forward or backwards, and print out all the answers. So this way, I don't even have to physically remove anything, and I guess it's faster. For this problem, it doesn't really matter as long as it's linear time, whether you use stack or this slightly faster approach, it really doesn't matter. So that's a sort of a different way of doing this. So I guess that's all I wanted to talk about. I guess it's actually right on time, huh? Okay. So let me just show you. Okay, so don't be alarmed by the fact that I have a lot of incorrect submissions, because the incorrect submissions are actually me taking other people's incorrect submissions and try to fix it. So you see, actually, the timing doesn't really matter which version I use. It's more or less the same. It's so small that it hardly matters. Anyway, so I guess that's it for this week. Now, next week, I have put in another. Oh, you already joined. You're faster than I'd say. Okay, so next week, this is 4 problems only. The problems are a little bit harder this time, and the theme is dynamic programming, and these are what I would call the standard dynamic programming. These are the ones that are sort of the textbook examples of what dynamic programming are. So even if you're, I don't know, are you guys learning this in 3620 at all? Not yet?
Yeah, we've just been learning that and greedy algorithms recently.
Oh, okay. So this is right time.
Yeah.
So you probably have seen some of these problems, and you know, you never learn something until you try to implement it. So here's your chance. So and then next week we'll talk about it. So the theme next week is standard dynamic programming. Okay, so I guess that's it for this week. And let me stop this